All right, coming back to inscribed angles for a second time here, just to refresh everybody's memory. Inscribed angles will always be half the measure of their intercepted arcs. So in other words, the arc at the top of the snow cone is going to be double the angle. Any two inscribed angles that intercept the same arc have to have equal measures, and that's because they're both half of the same arc. And parallel chords will intercept arcs that are equal in measure. And that came from the last homework problem, the last classwork problem that we just worked through. So let's take a look at a couple of things, a couple of exercises here, and continue our work with inscribed angles. So circle E, it's got a center point E. AB is parallel to CD, and that's marked with the arrows. Angle ADC is marked at 42 degrees, so all that's already there for you. And the measure of CD is twice the measure of AB. Okay, that part we need to mark up. So if CD is twice the measure of AB, then let's let AB be our x, and let's let CD be our 2x, just to show the relationship there. And we want to find the measure of arc AB. All right, so if we use this 42 to our advantage, if you can follow the rays on that 42 degree angle out, it's got an endpoint at A and an endpoint at C. So the top of the snow cone would make the intercepted arc. I'm going to take that inscribed angle and double it, and it's going to give me 84. Now alternate interior angles would tell us that there's also another 42 degree angle here. So following that one out, I've got endpoints B and D, so another subtended arc that would equal 84 degrees. So I've used up 168 degrees of the circle. So if I take 360 and subtract 168, at this point I am down to 192 degrees remaining. This x and this 2x represent the rest of the arcs in the circle. So that 3x has to add up to 192. Dividing by 3, I get x equals 64. And that tells me what arc AB is. So the intercepted arcs on the inscribed angles led me to have a remaining number of degrees that could be split in a 1-to-2 ratio. All right, exercise 2. In circle A, diameter BC has been drawn, so we've got that. We want to explain why BEC, BFC, and BDC are all congruent. And it's because they all intercept the same arc, so let's look at that. Angle BEC has, so B to E to C, that has endpoints at B and C on the diameter. BFC is another angle that has endpoints on the diameter. And BDC is yet a third angle with endpoints on the diameter. They're all inscribed angles. They all have a vertex on the edge, and they all end at the diameter. So they must all have the same measure. They're all half of a semicircle. Common measure, they're all going to be 1/2 of the semicircle arc, so 1/2 of 180, which is 90 degrees. All right, if the radius of circle A is 5 and BD is 6, find the length of DC. So let's see what we can do with that. BD is 6, the radius is 5. So if I have 5 for this radius, I have 5 for this radius, I have 10 total, right? And so if I want to solve for DC, let's put an X there. It looks like, what did we just say? That all of these inscribed angles are 90 degrees. So it looks like we have a right triangle that we can use Pythag for. So 6 squared plus x squared equals 10 squared. And if I subtract 36 from 100, I get 64, so x comes out to 8. Now this is very important here. When you are solving for chords in a triangle within a circle, you do not always have a right triangle. And I want to repeat that. You don't always have a right triangle. Right triangle strategies will only work if you have a right angle that you can be sure of. If the endpoints are the diameter, then you can be sure that it's a right angle. But you can't always be sure that every inscribed angle is a right angle, and so you need to make sure you have that before you can employ Pythag or SOHCAHTOA or anything else like that. All right, exercise 3. Building off of this inscribed semicircle must be a right angle that we just looked at. Then we're going to have all kinds of right triangles come up, and we're going to be revisiting all of our right triangle strategies that we used in the last unit. So diameter AC has been drawn. OC is 8, which makes AC 16. AB is 5. Find the measure of arc BC, so that's out here. Okay, well, if I knew, so this arc here, this arc BC, has endpoints at C and B. If I follow those segments back, I get an inscribed angle here at A that I don't know yet. But if I did know it, I'd be able to double it to get the subtended arc. That's the strategy. So we can use an inscribed angle to get an arc. How are we going to get this angle? Well, angle B is an inscribed angle on a semicircle because this is running right through the center. It's a diameter. So I can make a right angle symbol here, which means that my trig will apply. So the 16 would be the hypotenuse, the 5 would be the adjacent, and so the A and the H tell me to use cosine. So I'm going to do cosine of theta is equal to adjacent 5 over hypotenuse 16. So theta must equal inverse cosine of that fraction 5/16. Okay, if I do inverse cosine of 5/16, I'm getting approximately 72 degrees. And so that tells me that arc BC must be double that, which is 144 degrees. All right, so trig, Pythag, those things haven't gone away. All right, final piece we'll see in this lesson, talking about inscribed angles occurring within a quadrilateral. So if a quadrilateral is inscribed in a circle, what that means is all the vertices of that quadrilateral are touching the circle's edge. That's what it means to be inscribed. So if that happens, it's called a cyclic quadrilateral. Cyclic is that term. And so in this situation, in exercise 4, circle E, center point E, quadrilateral ABCD has been inscribed, so all 4 corners are touching the circle's edge, and the angles are listed as shown. So the relationship between the opposite angles, if we take 106 and 74, 117 and 63, what do you notice? Those opposite angles are going to sum to 180. So that means that they are supplementary. Okay, so why does this relationship exist in all cyclic quadrilaterals? Well, if you take this 106, for example, got endpoints at A and C, and you take this 74, it also has endpoints at A and C. So that means that one of these angles subtends the minor arc, and one of these angles subtends the major arc, which means in combination, they subtend the entire circle, so they'd be half of the entire circle when put together. Right? If one angle is half of part of it, the other angle is half of the rest of it, then when you put them together, they should be half of the whole thing. So to put that in more formal terminology, opposite angles raised intersect at the same points. We mentioned that. So the arcs intercepted by those inscribed angles constitute the entire circle. Since the inscribed angle measures half, then the sum of the angles would also be half of the circle. All right. Quadrilateral QRST is inscribed in circle W as shown. So we have QRS 12 degrees less than 3 times the measure of QTS. So it seems like QRS is based off of QTS. Let's put a 12 degrees. QRS is 12 degrees less than 3 times the measure of QTS. Right, so this angle here is, you know what, just for a second I'm going to take that diameter out. I'm going to put it back in, but just for a second I'm going to take it out, just to make it easier to see. Alright, I'll put that back in just a minute. QTS is related to QRS. Let's put an X in QTS. We'll put the rest of it, 12 less than 3 times, so 3x minus 12. Those two angles there are going to make up 2 inscribed angles in this cyclic quadrilateral. So they need to add up to 180. So I need x plus 3x minus 12 to equal 180. Right? So that's 4x. If I add the 12, 4x equals 192. And x comes out to 48. I'm looking for QTS. That's where my x was. So measure of angle QTS is 48. Okay? Common measure of RQT and RST, so this angle here and this angle here, well, this has to do with the fact that R, W, and T are collinear. We haven't used that fact yet. And that's where this line comes in. If R, W, and T all fall in a straight line, then that straight line runs through the center and is therefore a diameter. Well, angle Q is an inscribed angle on that diameter. Angle S is an inscribed angle on that diameter. And so, since they're collinear, RT is a diameter, and those angles are inscribing semicircles. RQT and RST would both be half of those semicircles, and therefore 90 degrees. So that term collinear was important to be able to figure out that last part. That's how we know that that was a diameter, and therefore a semicircle that it's subtended.